guess we're ready to get started. So good morning, everyone. Today we're going to be starting chapter 2. So we're going to start talking about communication within the nervous system, and what that means is we're going to start looking at neurons and how we transmit signals and things like that. So you might have noticed that I've broken this chapter down into 2 parts, and that's because I'm going to try and cover sort of some of what's posted today. It'll probably end up bleeding over into tomorrow, depending on how things progress. But this is a fairly complicated topic, so I want to take some time with it just in case. I'm also going to be posting some videos to our Moodle, just once I find stuff that I think matches really well with the level of difficulty, or the level of detail, we can say, that we use in our course. Because I find if you start looking up things like neurons firing, you can have very, very simplified models or very, very complex ones, and we're going to fall somewhere in the middle. So with all of that out of the way, let's start by talking in general about neurons. So by now you have probably figured out that neurons are the cells that convey all the sensory information up into the brain. They carry out operations sort of within the brain and the rest of the body, and then transmit commands out from the brain to the rest of the body. So we're going to focus in on the structure of these cells. We'll talk about sort of a general neuron, and then a couple of the different varieties of neurons. And then later in the chapter, we'll get into sort of the support system that exists for those neurons. But for the beginning here, most of this should be review, one would hope. So we'll start with talking about the cell body and the nucleus and the dendrites and the axon and the terminals and all of those things, and then a little bit about how each of those work and what they do. So this is probably, hopefully, what you think of when you think of a neuron. This is actually a bipolar sensory neuron. We'll get into the details as to why this one is bipolar, but this is typically what you think of. So one string of neuron where, let's see if I can get the mouse to go onto that side. So sort of one straight line there. So at one side we have our dendrites, we have our nucleus in the cell body, or the soma, in the middle there, and then we have our axon and then the terminals at the end. And these little red arrows are indicating the direction of transmission. So things are going to move from the dendrites to the axon and the axon terminals, unless something has gone catastrophically wrong. So the most obvious part of this, theoretically, is that cell body, or the soma, right in the middle. So it's basically like any other cell. That is going to be filled with cytoplasm and organelles. This is where things like the nucleus, which contains all of our genetic information, as well as other functional organelles like ribosomes and mitochondria, and all of those things you might remember from bio class. Those are all in that cell, in the center of the cell there as well. So just like any other cell, it needs all of these structures and the things in the middle that keep it functioning. But what we care most about with these neurons is actually what happens across the whole cell. So we're going to look at that in a little bit more detail. Let me just double check. I always forget. I'll put in a slide that has what each of the different areas is and what it does in general, and then I talk about all of it on this slide. So I take that slide out, and then I'm going to click ahead looking for my usual written stuff. But I caught myself this time. So before I move on, I'll go back to the dendrites at the beginning. Right there, those guys. And those are extensions that sort of branch out from that cell body, and they're going to pull in information from other neurons or from sensory receptors. So that's sort of like the antenna receiving the signal, and then it's going to pass it along through the rest of the cell, and then out towards the axon and the axon terminals. So the axon extends sort of like a tail away from the cell body, and that's going to be pushing that information, carrying that information from what the dendrites brought in to the cell body, and then out to other places. We also have those little, almost like a hot dog bun wrapped around the axon. That's called the myelin sheath, and that's basically there to insulate that axon, and it allows for faster transmission of signals and less of a degradation of that signal, so it's more for efficiency. Just like the insulation on an electrical wire, that's what the myelin sheath is doing. And then for the axon terminals, those little sort of swelling tip things are the terminals, and they're basically going to be areas where they have bundles of neurotransmitters. So there are vacuoles full of neurotransmitters that can be released outside of the cell, and the terminals of one neuron will empty out into a space that's in between neurons, and then at the other side of that space is actually the start of the next neuron, typically. So the axon terminals of one neuron touch the space that touches the dendrites of the next neuron. And so we can talk about them as the presynaptic neuron, so the neuron before that gap, and the postsynaptic neuron, the neuron after that gap. So that's typically the notation we'll use when we talk about those. And neurotransmitters, which I didn't define when I mentioned them, are just chemicals that the neuron's going to release to communicate with the next thing in the chain. And we usually assume a single chain of neurons, so one neuron to the next across that synapse, but a neuron can communicate with muscles or organs or whatever it's touching next in that chain. So though we think of sort of this straight line of neurons, it's a lot more complicated than that. All right. And so you should probably remember that there are multiple different types of neurons. So we're going to look at three major types. We have our motor neurons. So these are the ones that go sort of from the central nervous system out towards the muscles and organs. So they're carrying commands from that central nervous system outward. We also have our sensory neurons, which tend to work in the opposite direction. They carry information from the body, from our external environment, inward to that central nervous system. So that's where we're going to get, say, sensations. So you would have sensory receptors in your skin that will connect to sensory neurons that will bring that signal into your brain so that you can perceive what you are feeling. And then our interneurons are actually one of the more abundant ones, and these are the ones that connect different types of neurons. So these are the ones that are going to be doing all of the in-between work. Okay, I do have an image for that one. Okay. So with these different types of neurons, we have different kinds of structures, different kinds of appearances that tend to exist that will actually tell you what they are. So we looked at one of the examples here. So this one is what we had looked at previously for the most part. So that's going to be a motor neuron, but this one is a little bit different than what we just saw because this has multiple dendrites. So it's bringing in information from multiple places. So we would call that a multipolar motor neuron because it has multiple dendrites, and then it's connecting here to a muscle fiber. So that tells us that it's a motor neuron. So it's sending a signal out towards the body to do things. On this side, we have two different kinds of sensory neurons. We have the one that we were just looking at, which is bipolar. And so that's different from this multipolar motor neuron because our bipolar one only has one branch of dendrites, and then on this side it has the one axon. So there's only one axon, but we're quantifying it based on kind of the number of dendrites. I'm looking at it as how many connections are to the cell body. So this is bipolar, bi meaning two. So we have one dendrite and one axon coming out of that cell body. So it's a bipolar neuron. They don't specify what it's connecting to, but because they've told us it's a sensory neuron, we know that those dendrites are probably receiving information from some kind of receptor. If we move to the top one, this is called a unipolar neuron. Uni meaning one. So here we actually see something kind of interesting where our dendrite connects directly to the axon and kind of comes up into our cell body there. So this allows for very, very quick transmission because you don't have to propagate across the cell body. You can kind of skip that part and keep going into the axon. So a lot of our sensory neurons will have this kind of a layout, and I think of it as unipolar because there's only that one connection coming into the cell body. Ooh, yep. Yeah, so this is going to let us go fairly quickly. So especially when you see these unipolar ones, they're going to have that myelin sheath to allow for even faster responses. And they'll typically hop into the interneurons and then sort of spread that signal out. So it'll inform our brain, but it'll also immediately trigger a response in our motor neurons, which we'll have diagrams for when we get into like reflex arcs. And then for our bottom one here, these are our interneurons. So the interneurons are going to look very, very different from what you typically think of when you look at neurons. And that's because they have lots and lots of these branches spreading out. So they're going to look fairly different. This is sort of one example of an interneuron. They might have very, very short branches. They might have very, very long ones. But they're sort of just offering that connectivity and bringing in information from lots of places and then sending it back out again. So our interneurons don't quite follow our rule of sort of a clearly obvious dendrites to axon terminals that we can see and identify quickly. So usually if I'm going to show you an image of a neuron, it'll be either a sensory or a motor one, because those follow the quote-unquote rules that we stick with. All right, so we've talked about the fact that neurons are cells. They have different kinds of arrangements, but they're all going to operate in more or less the same way, despite having these different arrangements. So you may remember that the cell membrane is made up of a phospholipid bilayer. So you would have drawn sort of the little ball with two tails on it. So you have a hydrophilic head, which is that red ball on the screen, and then the two hydrophobic tails. So for the root there, hydro means water, philic means loving, so hydrophilic head means it loves water, it will dissolve into water. And the hydrophobic tail means that it's scared of water, so it tries to get away from the water that's in our extracellular fluid, as well as the water in the intracellular fluid. And so these properties allow these lipids to line up where the hydrophilic heads, the stuff that likes water, lines up on the inside and the outside so that it's touching all of these cellular fluids, whether that's inside or outside the cell. And all those hydrophobic tails, the ones that don't like the water, stick together in a clump. So those are going to be inside in the middle of our cell membrane. And that difference between things that can dissolve and interact with water and things that don't like water kind of keeps most molecules from passing through that. Because most molecules are either going to want to be in water or not in water, but not both. So it's really hard for things to pass through that passively. Things can sort of diffuse across the membrane, but for the most part, when that does happen, it's going to be happening in a fairly controlled fashion. So we might have something like these protein channels. So we can have channels that can be triggered to open, and so they'll allow molecules to flow through if they fit whatever criteria are required. So we might have a potassium channel, which when it's triggered to open will allow potassium to flow across that membrane. We also have things like pumps, ion pumps, which will use energy to specifically move certain molecules in a particular direction across that membrane. So with these channels, they're going to be triggered to open either by a chemical, so a hormone or a neurotransmitter or something like that, or they'll be triggered by an electrical signal to open. And so that's just going to be a difference in electric potential. And when that happens, they just open up and allow through what they're supposed to allow through. And then those pumps are using energy to establish a balance. So we'll think of things like potential energy and where things are stored when we start thinking about that movement. Because if it's allowing them to flow through freely, then we're making use of stored potential. But if we're using an active process like a pump, then we're going to be forcing things against what they want to do naturally, which is why it requires energy. All right, so for some of the terms that we're going to use by talking about energy and the cell membrane, we're going to talk about these individually because we're going to be using them pretty often. So we can talk about polarization, and that's a state where there's a difference in the electrical charge between the inside and the outside of a neuron. So with that phospholipid bilayer, with that system established where we control which molecules can move across the cell, we can end up with a difference in charges inside and outside. And by holding that difference in charges against where those molecules want to go, you're storing up potential energy. So we'll see things like resting potential in just a moment. So that's what it's referring to, is potential energy. It's like a battery where we've stored things in a state that is high energy. It's against where they want to be. And if you release that energy, it's going to move things in a particular direction. So by forcing this polarized state, we're storing energy across that membrane, which we can then use for things later on. And we can talk about voltage, which is a specific measure of the difference in electrical charge between those 2 points. Now, voltage can only apply to a difference. So you can only measure voltage if you measure the inside and the outside of the cell. You can't get a measure of the voltage of the outside of a cell. That doesn't make sense. Voltage is specifically that difference. It's trying to measure the polarization across that membrane, and it's trying to give us an idea of the stored potential energy. And that brings us to our resting potential, which is the difference in charge between the inside and the outside of the membrane of a neuron, specifically when it's at rest. That's why it's called resting potential. So when the cell isn't doing anything, once it's established that difference in charge across the membrane, once it's sort of sitting there, what does it sit at? That's our resting potential. And so the cell tends to rest with a slight charge across the membrane. So resting potential is going to be negative, and it varies. We typically see the number of minus 70 millivolts MV, but that's another one of those things where you're taught sort of a general rule, and then it kind of gets blurry in real life. But resting potential can actually differ depending on what kind of cell it is that you're looking at. So it can be anywhere between minus 40 and minus 80 millivolts for a resting potential. But again, our general rule of thumb that you will typically see is about minus 70. And so this is very, very small. This is not a large amount of energy. The textbook compares this to a 1.5 volt battery, and this is a 25th of the charge across one of those batteries. So it is a very teeny tiny amount of charge difference, but it is some stored energy that we can then use. All right, there we go. And so I've been talking a little bit about these particles that can move across the membrane, and the proper term for them is ions. So they are going to be atoms that have either lost or gained electrons. It's probably better, instead of specifying atoms, to specify molecules, because not all of the things that we're talking about are specifically one atom. So things like potassium and sodium are positives, the Na for sodium and K for potassium. Those are atoms, but things like our negative, the A minus, is just meant to indicate some kind of organic anion. So it's sort of a general term. It's not that A is an atom. It's not a specific element. It's just sort of a stand-in for a broad group of things that we're going to lump together because it gets too complicated. So we have our positives, so we have sodium, potassium, we have our negatives, which are chlorine, and our general anions, and we're going to end up with a separation at resting potential. So this diagram here is showing our, this is really hard to do, sorry, because I don't see what's up here. So that's our cell membrane there. On the outside, the extracellular fluid, because it's on the exterior of the cell, that's going to have mostly our Na plus and our Cl minus, just looking really close because it's a very bad diagram. But those red and greens on the outside, we end up with some sodium and some chlorine on the outside. And then on the inside, we typically end up with our potassium and our anions. So our K plus and our A minuses typically end up on the inside. And there's a little bit of sort of fuzz where there's a couple of the ones on the outside on the inside and some on the inside on the outside, but for the most part, that's what's establishing our resting potential. All right. So for the next part, the textbook starts talking about what kinds of forces are acting on these molecules and which direction are they trying to move. And so I have typically been against using PowerPoint animations because I find them really weird and finicky, but it is also one of the best ways to illustrate this, so I hope you can forgive the use of animations. So we're going to look at 3 different forces that are acting here. And some of these might make logical sense. If you've taken bio and chem, these are pretty logical things, but we're going to name them because they affect what's happening here in the cell. So we can look at the force of diffusion, and that's the tendency of ions to move through a membrane to the less concentrated side. So we can talk about things diffusing across that membrane, and basically what's happening is all of these ions are together and they don't necessarily want to be together. They're trying to push away from each other. They want to spread out as much as possible, and as a result, they're going to sort of equalize across that membrane if they can. As we mentioned, that phospholipid bilayer in the middle is going to block sort of free movement of everything, but some of the smaller things, like some of our smaller ions, can sort of move across a little bit. The next thing is electrostatic pressure, and that's when the charge, not just wanting to be away from your own kind of ion, comes into play. It's also the charges. So here I've had our potassium on one side, the K pluses, our chlorine Cl minuses on the other side, but this could include other pluses and minuses. This is just a simplified version. But for electrostatic pressure, we're referring to the force where ions are repelled from things that are similarly charged and attracted to those that are oppositely charged. And so that's going to work in combination with the fact that they want to get away from their own kind of ion and go elsewhere, but they're also going to be pulled to those negatively charged things. So we get that sort of movement across so that the electrostatic pressure equalizes as much as possible. Now, as I said, this isn't something that can just happen freely. They don't just all shoot through the phospholipid bilayer. There is some resistance, but that's kind of what I mean, where sometimes they will force their way through. But for the most part, when ions are moving, we're going to be using our sodium-potassium pump, so our Na and K pump, where for each sort of movement of our pump, we're going to bring in 3 of our sodiums, and on the other side, when it releases, when it goes in the other side of the cycle, it's going to expel 2 of our potassiums. So here they're shown as 2 separate pumps, but both would be operating the same way. So basically on one step, they bring in 3, and on the second step, they push out too. And so that's going to happen at all of the sodium-potassium pumps. So these are just large protein molecules, and they're going to move sodium ions through the cell to the outside. Oh, do I have them in the wrong direction? Give me a second here. This is something that I always do. I did do that. Curses. Okay, I always have to double check this, and I thought I double checked it, but I ended up second guessing myself. All right, while I have you here, I'm gonna move these arrows because that's the way it's supposed to go. All right, and I'll read it because winging it has not gone well. Okay, so these pumps are gonna move 3 sodium ions out, not in. I apologize. So these guys on this side are going out, and these 2 are going in. I apologize for the mix-up there. So this is that metabolic process where it's using up energy because those are moving against the gradient. So even though the positives want to be sort of inside and outside in equal measure, even though they want to sort of balance across that membrane, these pumps are going to push them in the opposite way. So we're putting out those sodium ions, and we're bringing potassium ions back inside to reestablish that resting potential. Okay. And I will go over that again one more time in the next class because I find as soon as I've made a mistake like this, it tends to throw people off. So I will come back over it again. This is what happens when I mix things up. So these pumps are actively working to establish that resting potential. They're actively pushing things against the way that they want to diffuse. They're pushing against the way that those electrical charges want to distribute. And so this is what's establishing our potential. The next thing that will actually allow for movement of ions, we were already kind of mentioning those, and those are the ion channels. And those are the gated pores that are in the membrane. Those are also proteins that basically act like tunnels that allow ions to move freely across that membrane in the direction that they want to move. So this is the way that that diffusion, that electrostatic force can operate when these channels are open. So this can allow the flow of specific ions to travel either into or out of the cell, depending on what kind of a channel it is. And so I already kind of mentioned that these can be chemically gated, which means that they're controlled by either neurotransmitters or hormones, or they can be electrically gated, which means that they're controlled by some kind of change in electric potential in the cell membrane. So as soon as one of those conditions are met, the channel can open up and allow things to flow through. So to stress, our sodium-potassium pumps are active. They are actively pushing things against the gradient. They are setting up that resting potential. They're creating potential across the membrane. They're creating that charge. So they're pushing out our sodium ions, and they're bringing in our potassium ions. And even though we would think that in exchange of sodium and potassium is fairly similar, they're both positively charged, what does the difference make? But remember that it's a movement of 3 to 2, which means that they're putting more of the positively charged things outside, and they're bringing in some positively charged, but not as many as they're pumping out. So we're ending up with a net negative on the inside. That's where that negative potential across the membrane comes in. So it's the difference between the two where the inside is going to be less negative or less positive, meaning it's more negative. And then the ion channels are not an active process. They stay closed until they are triggered. And once they are triggered, then they're going to open up and allow those molecules to flow back across the membrane in the direction that they want to go. So they want to get away from their own kind of ion. So they want to spread across by diffusion because they want to get away from their own kind. They're also pulled by those electrostatic forces because they want to get towards, so the positives towards the negatives and the negatives towards the positives. And each of these ion channels will specify what kind it is. So we might say that there's a sodium ion channel, and it is only going to allow sodium to move across that membrane. And because we were pumping sodium out actively, a sodium ion channel would then allow the stuff that was actively pushed out to come back in. Okay, hopefully that has fixed that. And as I said again, we'll go over it one more time next class just to help out. But I want to draw your attention back to our generic image of a neuron. And we talked about that idea that neurons are typically stimulated at the dendrites and or the cell body depending on the arrangement. So it's going to be stimulated on that one end on your left-hand side, and then the signal is going to move from the dendrite end of the cell towards the axon terminal end of the cell. And that direction is how that signal will move. So a signal can come from another neuron, it can come from a sensory receptor, it can come from sort of one of those sources that's going to be telling this neuron to pass on a message. And the effect, that signal that it's given, can either be excitatory, where it increases the likelihood of that signal being transmitted, or it can be inhibitory, where there's a decrease in the potential of a signal being transmitted. We typically think of signals being something that's excitatory only, where when the dendrites of a neuron are signaled, that it's going to lead that whole neuron to fire, to send along a signal. But that's not always the case. There are those inhibitory signals that will make it less likely for a neuron to fire. And so what we look at locally is the interaction of those excitatory and inhibitory signals and see what happens overall. So if a neuron is being told by some other neurons to fire and others not to fire, we're going to have to sort of find a balance in between and see if we push over that threshold to fire or not. And so that concept of firing is actually called depolarization. So that's our action potential. That's going to be the process of transmitting a signal along the length of that neuron. But as I said, we're going to be looking at sort of what's happening locally to see if we trigger something at the level of the whole cell. Now, I find that this is a little bit more detail than you tend to see in, say, intro psych. But it's not as much detail as you might see in like a cell bio course, so we're kind of riding that middle ground here. So you might have more knowledge than this, or this might just be sort of a step up from what your experience is. And that's why we take time with this chapter, because some people know lots more, some people don't quite know this much yet. It's either review or new, so we'll just go through it as we do. So when we're looking at that local potential, we're looking at sort of partial depolarizations. We're looking at changes in the charge across a membrane locally in a small area. So we're not looking at sort of the whole cell scale. We're looking for this one small area. And so with a local potential, the polarity in an area will shift usually towards zero when disturbed. So that shift towards zero, that getting more positive, because remember there's usually a negative potential there, as it gets more positive, that's that excitatory process. That's that being pushed towards fire. We can also see it moving in the other direction, where if we have an inhibitory process, we're going to move away from zero. We're going to get more negative and be less likely to fire. So that's what's happening locally. And so these local potentials, unlike what you might know about an action potential on the level of the whole cell, A local potential is actually a graded potential. And that means that it's going to vary in magnitude with the strength of the stimulus that produced it. Basically, how much excitatory or inhibitory stimulus does it experience? More excitatory stimulus leads to getting more positive or closer to zero, and more of that inhibitory stimulus is going to lead to it getting more negative. So this is called a graded potential because it can move, it can be graded higher or lower depending on what it's receiving. And so as I said, we're looking to hit a particular threshold that triggers a larger scale response, which I included a slide for. So if that local potential exceeds that arbitrary threshold for activating our electrically gated channels that are holding that charge across the membrane, then it can trigger a chain reaction that can affect the entirety of the cell. If we exceed that threshold, we will trigger an action potential that will travel from the dendrites or wherever it's being triggered all the way over to our axon terminals to the next cell. So this threshold, again, you're usually taught that our resting potential is -70. We have our range now that we know that there are different kinds of neurons in different situations, but the threshold is typically about 10 millivolts more positive than the resting potential. So if your resting potential is -70, then your threshold is usually about -60, so 10 more in the positive direction. And so we use our graded potentials at the local level to see, do we hit that mark? And once we hit that mark, then we trigger that action potential. And so this is probably the diagram that you are used to seeing associated with action potentials. So we have our -70 resting potential. We have our associated -60 threshold labeled here. Those numbers could be swapped out depending on which kind of a neuron we're looking at, but we're going to use sort of the generic for explaining the process. And so our red line is showing what the electrical potential is at any given time. Our x-axis isn't labeled, but that's just generic time. So our action potential is an abrupt depolarization of the membrane that's going to allow the neuron to communicate. So it's that abrupt shift in the electrical potential, it's that firing that then propagates along the length of the neuron and allows us to send that signal to the next neuron in the chain or to the muscle that we're trying to trigger or whatever is next in that place. And so here we have, I gotta do this, there we go. So we're sitting at -70. If our local potential ends up hitting that threshold, that right there will trigger, that's sufficient to electrically stimulate the opening of those electrically gated ion channels, which will then allow for ions to flow into and out of the cell appropriately. And it leads to this depolarization where we go from being very, very negative to being, in some cases, quite positive. Again, these numbers will shift depending on which cell we're looking at, but typically in the range of positive 30 millivolts. So we see a swing of almost 100 millivolts from our resting potential to the peak of our action potential. And then everything will sort of recoup on the other side and get us back into a resting potential. Now, before we talk about the specifics of what's leading to each of those different stages, I just want to talk about the difference between action potentials and local potentials. So our action potential, unlike the graded local potential, action potentials are ungraded. Ungraded meaning that it isn't going to change in magnitude based on the signal that comes in. So with action potentials, we have what's called the all or none law. And this basically says that action potentials will occur at full strength or they won't occur at all. So if we hit that threshold, if we get to the point that those ion channels can open, then the whole cell is going to fire, the process is going to go along the length, or we won't hit that threshold, they won't open up, and it won't trigger a full-scale response. Yep. So we're going to have on the next slide, we're going to talk about sort of the order in which they open. So it'll be that one specific kind of ion channel opens at first, and then the next kind will open, and that'll sort of move along our neuron in a process. So yeah, we'll talk about the specifics in as much detail as we need. And again, there are more levels that could be discussed if you were in, say, cell bio, but we don't go that far, thank goodness. So we can say that our action potentials are ungraded, but we can also say that they are non-decremental, and that basically means that they travel along the axon without any decrease in size. It means that they're not going to get smaller with time. It means that an action potential triggered here is going to trigger an equally large action potential in the part of the cell membrane next to it, which triggers an equally large one in the part next to that, and so on and so forth along the whole length. So we have this propagation at each successive point along the membrane all the way down that axon, so that strength is maintained. The sort of pattern that we see in that graph is going to stay the same no matter where you are throughout the cell. So that's what we mean by non-decremental. And by having that, it allows us to transmit this information across fairly long distances. So you can think of, say, getting the sensation of having your toe stubbed. Those sensory neurons are bringing that information all the way from the bottom of your foot into your brain. That's quite a long way to go. And the fact that these action potentials are non-decremental means that you're going to get that sensation passed all the way through, whether we want it to or not. All right, so now we're going to look at the sort of specifics of what's happening here. And I do find that this is really difficult to do with pictures, so I will be posting a couple of different videos up on our Moodle after class, just so that I find ones that give us a good idea of this, because I find sometimes getting stuff to move and interact gives a better picture of this. So if this doesn't quite work for you, don't worry, I will have more resources. And like I said before, I like to go back over this information a second time, just because it's a lot. So at the beginning of the next class, we'll probably do this again as well. All right. So for this diagram here, they're basically breaking down each portion of that action potential graph based on what's happening with our channels. So we talked about the fact that our ion pumps establish that resting potential, and then we're sort of sitting at resting potential. We're not going to be doing too much. So we would say that our sodium channels, the ones that are red, and the potassium channels, the ones that are blue, they're all going to be sitting there closed at resting potential. So the pumps have established that charge across the membrane. There's not a ton of movement across despite those forces that are acting. Everything's just sort of sitting with that net -70 potential across the membrane. So once that has occurred, we can then look at what happens when a local potential comes in. So we start receiving signals from nearby neurons or from a sensory receptor or something like that. And it's going to start giving a signal to that part of the cell membrane. And so just to sort of give you an idea of what we're looking at here, we're only looking at 2 of our ion channels in one very teeny tiny section of the cell membrane, but the whole cell is covered with these channels. There are many channels throughout the cell, all around the outside. We're just sort of looking at one very focused spot, and we're looking at sort of one place along the length. So just keep in mind that that's our perspective right now. And so that local potential, in this case, we're going to be looking, as almost always, at an excitatory potential, where we're going to increase the charge. We're going to get closer to zero. We're going to get less negative. We're going to move closer and closer to that threshold. And so that's going to partially depolarize the membrane, but if it doesn't reach that threshold, it isn't enough of a difference to trigger those channels to open. If, however, we start receiving enough of those excitatory signals, if the charge starts changing sufficiently, then it'll trigger the channels to open in a particular order once we hit that point. And so that's what our second picture there is showing. So for an action potential, once we've hit our threshold, that local potential has hit our threshold and it triggers our sodium channels to open. So our sodium channels are electrically gated. We've hit the criteria required to open them, and they open up. And so what this is doing is very, very quickly allowing our sodium ions to flood into the cell. And so as we can see in the graph, we get a really quick climb in the electric potential across the cell membrane. And what's happening there is that the inside of the cell was net negative to begin with. It was more negative inside than outside. But by opening that channel and allowing those sodium ions to come back into the cell, we're now getting the inside to be more and more positive. So this is where we're having things like our diffusion across, and even a little bit of those electrostatic forces because the inside was originally more negative, so the positives want to come inside. So we get this massive influx of positive ions inside, and that's what triggers our action potential. So the membrane in that specific area ends up depolarizing, and it actually ends up going so far that we go past a neutral charge across the membrane. That motion, that, momentum, there we go, across that membrane leads to us going too positive. That's why we get into the positive charge there, where we're up to, say, plus 30 millivolts across that membrane. We're saying that all the positives that could come in have come in very, very quickly, and now the cell is way too positive. And so once that's happened, the sodium channels will start to inactivate. We're now no longer at the correct electrical charge for them to stay open. This process has brought in too much positive, and now they're saying, nope, we're done, we can't operate, they shut down. So you'll notice that our red channel is now closed off again. And at the same time, our potassium ions, the blue channels, those potassium ion channels, are going to open up. Because it's very, very positive inside, now the positive potassium wants to get away from all of the positive sodium that has rushed in. So because our sodium channels are now closed, the sodium is stuck inside the cell. It can't go anywhere. But with those potassium channels open, the potassium can leave. So it's going to be pushed away from all those other positives. It's going to rush across the membrane. And that's when we see that drop off there in our charge. So we're going back to being negative again because all of those potassiums are flowing out. They're trying to get away from the other positives, and then we end up being net even more positive than when we started. So this process is repolarization because we're getting back to a negative charge. And again, we see that the momentum of that movement actually ends up overshooting where we wanted to be, and we end up more negative than our resting potential was at the beginning. And so there's a period where all of this rushing in and out has happened, the cell is in chaos, and the cell wants to get back to its homeostatic point. It wants to get back to that resting potential. So our potassium ion, or the potassium channels will close, so it stops that free movement of ions across the membrane, and now our sodium-potassium ion pumps will kick into play. And so these are the ones that are going to use up energy to get us back to where we were originally. So it's going to manually push those sodium ions out and pull those potassium ions in, and it's going to do so to the extent where everything that rushed in gets pushed back out, and everything that rushed out will get pulled back in, and we reestablish our resting potential. So that process will take just a little bit of time, and while that's happened, the cell stays too negative until we recover, until we get back to where we should have been. And so you might remember that when we're in that too negative phase, we are also in what we can call the absolute refractory period. And so this isn't just driven by the fact that the cell is too negative. This is also because for a certain period of time after they've been activated, when those sodium ion channels have opened and reclosed, they cannot be reopened. There's sort of a hard rule where they can't open again to stimulate a new action potential. There's like a timeout mode on them to turn back on. So that absolute refractory period is a hard rule where a new action potential cannot occur no matter what. There is also a relative refractory period. And this is what happens after that hard timeout with the sodium ion channels. So they have turned back on-ish. They're available to be triggered again. But because they just went off, and because we're in that too negative part, we actually have to have more of an excitatory influence to get back to that threshold to cause the next action potential to trigger. So once we're out of that hard, locked out, absolute refractory period, we end up in this relative refractory period where they could fire again, but because our potassium channels are still open, because we're still making the inside too negative, it's actually very, very difficult to trigger those sodium ion channels to open again. So a new action potential could occur, but only if that new stimulation is sufficiently strong enough to overcome the process that's already happening. So if I scroll back here, and if I find my mouse, that would be in sort of this period here, where we're not quite back at our resting potential, and the potassium channels would still be open. So I guess it would be just before that last arrow-ish kicks out, so somewhere in there. We're saying that if you could have a really, really strong push towards that threshold, a really, really strong push to get more positive, then you could trigger another action potential, but it's very difficult to do so. And so this combination here of the absolute refractory period, our hard rule on how quickly they can fire, and that relative refractory period where we can fire but only if it's sufficiently strong, actually determines how quickly a neuron can fire, and we can turn that into information on how intense a signal is. I saw a question? Yeah, like we don't put like a hard line on where it is because it kind of depends. So we put it as before the potassium channels are closed, that's when we're going to transition over into that relative refractory period. So the potassium channels are still open, so there's still kind of a free flow, and that's why it's really hard to push past that. And this is kind of weird because, as I said, usually we only talk about, at least in intro psych, about an absolute refractory period, and this is sort of adding that extra level to it. And my understanding of it is it's really hard to pin where it happens, and I think it ties into the extra processes that are going on that we conveniently ignore for this class. So yeah, the hard cutoff there is the potassium channels are still open, but we're past the absolute refractory period. And that's as much detail as you'll need to know about it. Cool. Oh, Yes. Okay, and so with that sort of how quickly we can versus cannot fire actually brings us to the rate law. And so this is saying that our axon will actually tell us the intensity of a stimulus not by the size of an action potential, but in its firing rate. So sometimes there's a common misconception that when something is more intense, maybe it feels more hot or more painful or more something, that must be a larger action potential. But as we talked about, our action potentials are that all or none, where they're going to happen at the exact same rate. They're going to fire fully no matter what, and they don't change size, so they're always going to be the same magnitude. So the magnitude of the action potential or the size of the action potential doesn't tell us anything because it's always consistent. However, between that absolute refractory period and that new relative refractory period, we know that if something is intense enough, the neuron can actually fire just that little bit faster than it should be able to otherwise. And our brains can interpret that increase in firing rate as an increase in intensity. So our rate law lets us convert how quickly we are receiving that signal, how quickly our neurons are firing, and turn it into sort of a intensity, or how much of this sensation are we getting. So we are restricted based on the absolute refractory period. That's how much space needs to exist between firing. And then the relative refractory period gives us a little bit of wiggle room, where if it's a less intense stimulus, we're going to see a longer period before it fires again. But if it's a very, very intense stimulus, as soon as that relative refractory period starts, we can start seeing firing again. And so that sort of shift gives us that intensity. Yeah?
So if it's a less intense sensory thing, and then a really, really intense one comes in, it's still fire? Or will that super intense one?
It depends on where we're at. If we're in the absolute refractory period, then it won't fire because it can't. But if it's intense enough and long enough that it lasts past that absolute period, then as soon as the relative refractory period starts, then it can fire. And so we would go from, I had a bunch of really slow firings to, oh, they're coming really quickly now, and we would perceive that as a change in intensity. So, and this is happening, like we're talking about it as, you know, oh, it's firing, and then it triggers the next one, and the next one, and the next one, but we're getting like hundreds of signals very, very quickly. So it's a much smaller time scale than what we tend to envision it as. So yeah, it'll be quite quick. Cool. All right. Oh, and I did put down some numbers for those who are curious. I don't like testing on numbers, but the absolute refractory period usually is about 1 to 2 milliseconds. And that limits us to a maximum of 453 firings per second in humans. And that's just an FYI factor, as opposed to something I will actually test on, but I find it interesting. And that will change based on different species, and of course there's a little bit of fuzziness depending on what kind of neuron we're looking at, but for the most part, that's what it is. All right, so that was a ton of information, like I said, and that's actually half of the content for this chapter, which is why I'm going to release us just a smidge early today. I will refresh some of those more complex topics in brief at the start of the next chapter, but then we're going to move on and talk about glial cells and other support system things then. But I will see you on Thursday.